Hello everyone. Today we are going to understand integration. So we already know that integration is the area underneath a curve, but we don't really understand how the theory behind it works, or the kind of the thought processes we have to use in order to arrive at what the area underneath the curve is. And so in today's video, all you really need is a basic understanding of differentiation and a bit of physics knowledge in kinematics. This means you need to know about displacement time curves and velocity time curves. So let's get straight into it. Now consider this velocity time curve. Well, it's not really a curve, it's just a straight line. Now what this tells us, what does this tell us? This tells us that there's constant velocity over time, which means that the corresponding displacement time curve of this will be a straight increasing linear relationship. It'll be something like this. And we know this is true from our knowledge of differentiation. We know that when you differentiate a straight increasing curve, straight increasing line, you get a straight constant value for your derivative. And so we know that the derivative of a displacement curve, the derivative of a displacement curve is our velocity curve. Because as you can see here, as displacement increases at a constant rate, and that is why velocity is constant. So we know that the derivative of a displacement is velocity. So if the derivative of this is velocity, so if this is the derivative, this, if you go the other way around, that must be the antiderivative. So we can establish that the derivative of displacement is velocity and the antiderivative of velocity is displacement. So that means to go from here to here, I need to find the antiderivative, which would be, to go from here to here, I need to find the derivative, which would be velocity. And to go from here to here, I'd have to find the antiderivative, which would be finding displacement. So it's quite well established. Now, another thing we know is that I can find displacement using this graph. And how is that? That's by finding the area underneath the graph. So what that means is, let's say I want to find this displacement that it did in this much time, in t time, and it has a constant v velocity. Now, we know that the area underneath a vt graph is displacement. And why is that? Because look, velocity is measured in meters per second, and time is given in seconds. So when you multiply these two quantities, meters per second times second, you get meters, which is the quantity for displacement. So by multiplying time and velocity, you get your displacement value. So we know that the area of a velocity time graph is equal to displacement. Now what this means is that if I want to find out the change in displacement, I can either calculate the area underneath the curve, or I can just look at the points over here. So I can take this point and I can take this point, and this will be my initial displacement and this will be my final displacement. So I can do area underneath Vt, which is the same as my final displacement minus my initial displacement. So the area underneath this curve is the same as subtracting these 2 points, because this will give me the change in displacement, and subtracting these 2 points will also give me the change in displacement. So now we've established most of the base that we need in order to understand integration. We know that the velocity is the derivative of displacement, and displacement is the antiderivative of velocity. And so that means if I want to go from velocity to displacement, I must find the antiderivative. And we also know that there are two ways to calculate displacement. One is finding the area underneath this curve, and the other area underneath the velocity time curve, and the other is by subtracting final velocity with initial velocity, final displacement with initial displacement. So these are the two ways you can figure out your change in displacement. So note this down, and then next I'll show you how where integration comes in and how it works. Now notice that the velocity time curve I gave you, or the velocity time line I gave you, because it was just a straight line, was a basic shape. It was a rectangle. It was something along the lines of this, if you remember. Now if I want to find an area underneath this line, it's as simple as multiplying this by this, because it's a rectangle. But when you're looking at velocity time curves, they're not always this simple, are they? Sometimes they can be complex curves, like something like this. And so then when you're asked to find the displacement, or you have to calculate the area underneath this curve. But you don't know how to calculate the area underneath this curve. And this is where the problem is. This is where we need integration. Now, let this velocity time curve be equal to y equals 3t squared. Let this be the formula of our curve. Okay? So we're going to have to work with this to find the displacement. This is all we've got, and we have to find the change in displacement between 0 and 4 seconds. This is the problem we're facing. Now, going back to what we discussed before, is that the area underneath a velocity time curve is the same as final displacement minus initial displacement. But what we're given here is the velocity time curve. We haven't been given initial and final displacement. We haven't been given final and initial displacement, sorry. And so somehow we have to use this curve in order to figure out what the displacement curve was. So now going back to the antiderivative and derivative we also studied, is that we know that if displacement is given by f of t, then velocity will be given by f dash of t. And we know that right now f dash of t is 3t squared. Now you may ask why this, because we know that velocity is the derivative of displacement, and so if displacement is given by ft, velocity will be given by f dash t. And we know that f dash t is 3t squared. So we somehow have to find the antiderivative of 3t squared. So what original function do we differentiate in order to get 3t squared? And if you studied a differentiation and power rule, you'd know that this basic function would be t cubed, because you'd have t cubed, and the cubed would come down, 3 would come down, and you'd minus 1 from the power, so you get 3t squared. And so you know that your displacement function will be given by t cubed. Now, if you've noticed, when you differentiate something, when there's a constant, like imagine we did 3t squared plus 3, and this was f of t. Just imagine. If we were to differentiate this, we'd get f dash t, and if this was t cubed plus 3. So if we were to differentiate this, we'd get 3t squared, and then because there's a t to the power of 0 over here, this is imaginary, like it's there, it's t to the 0, but it's not written explicitly, so you can put this in. The 0 would come down, and then the whole thing would be multiplied by 0. So we're not sure if there's a constant, so we'll just write t3 plus c, because there might be a constant which we are unaware of. Okay, so now we've got the displacement, we've got the function for the displacement, which is t cubed plus c. Now we're given the task of finding the displacement of between 0 and 4, the change in displacement between 0 and 4. And if you remember, change in displacement is given by final displacement minus initial displacement. So our final displacement is given by subbing in 4 for t, so 4 cubed plus c, and our initial displacement is given by subbing in 0. This equals 64 plus c, and this equals c. Now when we subtract this, we get 64 plus c minus c, because we're subtracting the c value, which is 64 meters. So what we found is the change in displacement. Now note that this, we established before, that this change in displacement is also the area underneath the curve. So area underneath the VT curve. So we found the area underneath the velocity time curve, and that is 64 meters. And this is how integration works. And now I will explain this using the mathematical symbols and what integration and the formula or the notation of integration. So we know that 64 meters squared. So our original, so our displacement was given by t cubed, and our velocity was given by 3t squared, and our area was 64. Now, if you take out all the physics out of it, if you take the physics out of this demonstration, what we pretty much did was that we had x values and y values, and we had a function which was 3t squared, or 3x squared in this case. And we found the area between 0 and 4, between x equals 0 and 4. So how would you write this in the mathematical language of integration? So you're finding this area, and so you'd integrate it. Now there's a notation for integration, which is the sum of all values between 0 and 4. These are our limits. The lower limit always goes on the bottom, and the upper limit always goes on the top. So these are our limits, and we're supposed to find we're supposed to integrate this. So our function is given by 3x squared. And when you find the area underneath the curve, when we write this, what we're writing is that for every small change in our x values and the height, so what we're doing is base times height. Now height is given by 3x squared, and base is given by small change in x. Delta x means small change in x. So our height is given by 3x squared, and for every small change in x, which is delta x. So 3x squared delta x. Now what we have to do is find the antiderivative of this function. And that we figured out was to be t cubed, or x cubed in this case. Now remember, we had our limits, so we will write them as like this now. Now we're gonna sub in these values. So 4 cubed minus 0 cubed equals 64. And this is how you write it using integration terminology. Now going back to what this means. So this big curve means the sum between 0 and 4, and then area of a rectangle is given by height times base. So your height in all of these cases is given by the function 3x squared, and your base, well, what you're doing for your base essentially is creating really tiny values of x, of length of x, in which you can create really small rectangles, which is technically really small rectangles, but it's just integration, and it gives you the right answer. So 3x and then dx, which is your really small changes, and so that's how you get, that's what this means. And you want to put a bracket around this, especially if it's something complicated like 3x squared plus 3x, then you want to definitely put a bracket. But yeah, so this is how you write it in integration notation, and this is how integration works. I hope you understood how integration works, and if you want, you can try with another example, which I'll give you. We can do another one with, do 4t cubed and between 0 and 7. So you can find the area underneath the curve between 0 and 7, and your function is given by 4t cubed. So yeah, that's it for this lesson. I hope you understood how integration works, and you understood how the notation also works, and I hope you had a good time watching this video. Thank you.